I'll begin with a word of prayer. Ahem. All right. Heavenly Father, we thank you for this day. Thank you for this class. Just pray that you with us. Help us to glorify you what we do. And just understand a little bit more about physics today, Lord. In your name I pray, Lord Jesus. Amen. All right. So let me give you guys an example. Work this one out here by hand. And so, somewhat similar to one of your homework problems. Let's see here. So, example 1. Suppose that the acceleration is given by minus, let's say, beta v cubed. All right, so given the velocity is equal to v naught when t equals to 0, and x is equal to x naught when t is equal to 0, find the velocity as function of t and then x. All right, so we want to find the velocity both as a function of time and also as a function of position. So I'll start with the time. And so here's how that goes. Acceleration. And so this is, context here, because this is the only context I can ask this question in its current format, is the one-dimensional context. So we're assuming one-dimensional motion. So it might be motion along a line, or horizontal or vertical, I suppose, or whatever you like. So okay, so here we go. We have the acceleration is dv dt, right? But that's also given to be minus beta v cubed. So the way to solve a problem like this is to do what's called separation of variables. So this gives us dv over v cubed is equal to minus beta dt. Okay. So then you integrate this thing. All right. And so if we integrate both sides, I'm going to integrate over corresponding bounds. I'm going to integrate from v naught to vf. And over here I'm going to integrate from time 0 to time tf for final time. So what's the integral of 1 over v cubed? I'll start you out. Minus 1 over what? What? Yeah, 2. We're looking for a 2v squared, but I'm going to put a vf squared here because I'm going to do the fundamental theorem of calculus. So I have minus 1 over 2 vf squared plus 1 over 2 v naught squared. But yeah, the integral to the minus 3 power is minus 3 plus 1, which is minus 2, divided by minus 2. So that's just the power rule. And then on the right-hand side, that's easier, right? We just get what? Minus beta times the final time. So then if I do a little bit of algebra here, I have 1 over the final, let's say 1 over v squared is equal to 1 over v naught squared plus 2 beta t. And so just to let you know what I'm doing here, what I'm doing is I'm putting vf equals to v, and I'm putting tf equals to t, just to make that step. And then I'm also just rearranging and multiplying by 2, right? Yep.
We're doing the fundamental theorem of calculus here, right, with the integral?
Yeah.
Would the final velocity minus the integral?
That's what I did, yeah. So minus a minus is a plus, yep. So then, yeah, it's all good. So this then is v is equal to, plus or minus 1 over the square root of, 1 over v naught squared plus 2 beta t. And if you think about that for a minute, if we multiply the top and the bottom, so the plus and the minus should be governed by what? It depends on the sign, right? Like, is the initial velocity positive? Is the initial velocity negative? If it's positive, I go with a plus. If it's negative, I go with a minus, right? But you could just rewrite this formula like follows. This is V0 over the square root of 1 plus 2 beta t v naught squared. If you think about it, that makes sense. See, because the sign of this formula, it's going to be negative if v naught is negative. It's going to be positive if v naught's positive, right? And if you plug in times 0, what do you get? What happens if I plug times 0 into this formula? I get back what? V. So to be clear, this is velocity at time t, if you want me to be explicit here. So there you go. This is the answer to part of my question. That's the velocity at time t. So I'll try to write higher in the next part. So I should start selling like periscopes. I'm thinking of adding merch to my channel. Maybe I could start selling classroom periscopes, something like that. So next up, we have A is dv dt, but we can also write that as dx dt, dv dx, also known as v dv dx. So v dv dx is another way we can write the acceleration. And if we want to solve for the velocity as a function of position, we want to set v dv dx equal to, in this case, minus beta v cubed. Now, I go through essentially the same calculus I did in the previous story arc, right? Oh, laptops in the back need to be put away. Thank you. So, opening the notes. All right. So, but this isn't in the notes. So, okay. Anyway, so we need to then do what? This gives us dv over v squared equals to minus beta dx if we separate variables, right? So we separate and then you integrate. So this one's a little bit different. Notice that before we had a division by a cube, now we've got division by a square because this copy of v here cancel out, right? So it's related but different problem. And all right, so now we integrate both sides. We're integrating, say, from v naught to vf, and I'm going to integrate this from x naught to xf. And so what I got is I've got minus 1 over vf plus 1 over v naught is equal to minus beta times xf minus x naught. Right? And then I'll set vf equals to v and xf equals to x rather, and that gives me 1 over v is equal to 1 over v naught plus beta times x minus x naught if you do the algebra here, which then flipping it gives us v is equal to 1 over v naught plus beta times x minus x naught, which I think we can do a little bit more algebra to clean up. One more step here. I'm going to clean this up. This is v is equal to, say, v naught divided by v naught plus beta times x minus x naught times v naught. So that's a reasonably pretty formula. I think that's wrong.
Where did the negative on beta go?
Oh, so if I... that's a good question. I'm adding this to the other. So basically I'm taking this and moving it over here, and I'm taking that and moving it over there, and then flipping. I mean, however you want to look at it, but the point is, if you do algebra, you can get from here to here. So you notice that 1 over VF and 1 over V naught should have the same sign if they're on different sides of the equality, since they have different signs if they're on the same side of the equality. And so, anyway, algebra. Now my boxed equation's wrong. Tell me why. Yeah.
You have V naught in every term in that fraction.
Right. So why is that wrong also? I mean, how do I get from here to here? What was I trying to do? But I almost did, but I didn't quite do it successfully. What's the algebra step here? Yeah, multiplying by 1, right? Multiplying by V naught over V naught. And when I do that, what should happen? I get a V naught up here. Yeah, and I get this V naught here, right? But it distributes through, and 1 over V naught times V naught is 1. That should be a 1. And it had better be, right? What happens now with my formula? If I set x equals to x naught, does it make sense? See what happens if I put x equals to x naught? That term is 0, and we're just left with v is equal to x naught. So to be fussy here, this is actually v as a function of x. All right? So one of the problems in your homework is just like this. I ask you to find the velocity as a function of position and the velocity as a function of time, given that you know the initial velocity is v naught and the initial position is x naught. So you need to go through a thought process very similar to what I just did here. All right? So there's that. I just thought it would be healthy for you guys to see me write it out as opposed to just point at it with the projector on this particular problem. So that said, I've got some more things to project for you. So while we're waiting for the projector to warm up here, I will tell you a joke that I heard when I was visiting my wife's family in Brooklyn. I was trying to escape. My wife's family, their apartment is like 600 square feet, but there's like 7 people. So it's not good. You know, it's not good. So if you have like a really, popular roommate and you live in the dorm and all of their friends are over and you're trying to study, you know what I felt like if I was trying to work in the, it's not good. So I try to escape to go to, like Dunkin' Donuts, of which there are many in Brooklyn. And come on, work. So I'm sitting there, minding my own business, and there's these neighborhood punks come in. They start harassing the employees, right? And they're just causing trouble. They're just up to no good, these kids. And this old feller, he takes an interest to one of these punks, and he says to him, he says, "Hey, son," and he gets his attention. Yeah, he's like, "What's your favorite subject in school?" And the kid's like, "Oh, math, I guess." And he's like, "Oh, really? I got a question for you." And the kid's like, "All right," so he's listening. And so the guy starts. He's like, "All right, you paying attention to me?" And the kid's like, paying attention. He's like, "Yeah, sure, I'm paying attention." And sorry, I got to find something here. And so the guy starts into his story. He's like, "All right, so there's a subway car, right? In the subway train, there's 5 people on the car. You got that?" And the kid's like, "Yep, got that." He's like, "All right, so the car makes a stop." "Yep." He's like, 3 people get on the car, 1 person gets off. You got that? Kid's like, "Yep." And then he's like, "All right, the car goes, subway goes down the tracks, and I can't find my notes. I'm not very good at multitasking, but I'm going to keep telling this joke. So goes down the track and stops again, right? And then 4 people get on, 7 people get off. You got that?" The kid's like, "All right, got that." It's like, so then the car makes the next stop, and no one gets off or on. All right, it's fine. And then it starts up again and goes down the track, and then 2 people get off, nobody gets on. All right, great. And it goes on like this for about 5 minutes. All right, goes on like this for about 5 minutes, and then finally the guy's like, "Are you ready for the question?" The kid's like, "Yeah," and he's like, how many stops did the train make?" I love that. I mean, this old fellow, he executed this joke in a better way than me, but I love that joke. So that's my preamble to the subway example in my notes, which I will eventually get to if I can ever find my notes. Sorry guys, I cannot find it. I've got the notes open on my computer in the office, but you know what? That doesn't help us here. Just a second. You guys have any questions while I'm hunting?
Our first test is next week, right?
The first test is next week. Those sound like true words. Which day next week? Do you guys know?
Wednesday.
Wednesday.
And mission 1 is
That
Monday.
that rings. I would say yes. Mission 1 is collected on Monday. That I would agree with. Yes, mission 1 is collected on the 3rd of February, also known as Monday. That is true. All right, so here we go. Where was I? So we talked about some of these things here. So this problem right here is my subway car problem. The subway car accelerates as it leaves the station, all right? And what are we told here? The subway car leaves the station. I should have brought my glasses. I'll have to get over here where I can see it. And it accelerates down the track, right? Now, what are we told about it? As it passes a person, see this is the person right there, waiting for another train, it takes 2 seconds for one car, 1 second for the next subway car to pass. If the cars have length 10 meters, then how fast are they traveling as they begin to pass the person? So here's the situation. Time 0, like this. After 2 seconds, the first car has passed. After an additional second, the second car has passed, right? So then the question is, how fast are they traveling as they begin to pass the person? In other words, the question is, what is the initial velocity? So this problem, if you try to attack it with a lot of the equations we looked at last time, it'll confound you. You have to use the average velocity formulas to solve this problem, as far as I know. So the way we look at it is the average velocity. The average velocity in the first instance is, it goes 10 meters in the first 2 seconds, right? So for the first 2 seconds, 10 meters go past, 10 meters of car go past the person, right? So the average velocity is 10 meters divided by 2 seconds over the first 2 seconds. So I get 5 meters per second. But on the other hand, it's also the average of the initial velocity and the velocity just as the car is passing, the first car is passing the person, which I'm calling v1. But then I can also calculate the average velocity over the final second, right? During which time the train goes another 10 meters past the person, right? So 10 meters per second is the average velocity over the last second. But it's also equal to the average of the middle velocity and the final velocity, right? But then I can also look at this in the totality of both cars, right? Both cars pass the person, that's 20 meters, and it takes 3 seconds for both cars to get past. So I can also calculate the average velocity over the totality of the 3 seconds in play here. And I get 20 meters divided by 3 seconds, which gives me 20 meters per second, but that's also equal to the average of the initial velocity and the final velocity. And there you go, I've got 3 equations and 3 unknowns. You do algebra, and out pops 1.667 meters per second. This is a nasty problem. This is a nasty, nasty problem. This one, on the other hand, is pretty easy. Next example here. Suppose you have a rocket car. It accelerates from rest. So in your homework, I neglected to tell you it goes from rest. Which problem was that in the homework? See if I can find it right quick. One of you was talking to me about it today, and I noticed I was you asked me about this, and I was like, 13? Here, a rocket car accelerates with a net force of 4 times its weight over a distance of L. So what I forgot and neglected to say here is the car starts from rest. That is to be assumed here. I think if I didn't tell you that, the problem doesn't, well, maybe the problem has infinitely many solutions. So I do want it to have a single solution here. Not every problem has to have a single solution. There can be problems that have infinitely many solutions, but this is not one of them. You should assume for problem 13 that the rocket car there starts from rest. All right, so getting back to the notes here. if we have a rocket car accelerates from rest at 2g over a distance L, then it releases its air brake, which decelerates the car at minus g and comes to rest. How far did the car travel? I'll draw a picture for you guys. All right, so here's what did I say? Accelerates at 2g, a distance L. So this is the distance L, right? Then what happens? It's decelerating, so we have the initial velocity is 0. This velocity I'm going to call v1. And it's a decelerates at minus g until it comes to rest. How far did it travel? No, rest. Did I say what this distance was? Or I just said a was minus g. Oh, the question is how far did the car travel, right? Okay. So how would you solve such a problem? It's got two steps, right? They're both constant acceleration. So we should probably use the constant accelerations formulas for this one. And so let's do that. So we know L too, right? So like for this first step in the journey, we can say v1 squared, right, is equal to v naught squared plus 2g times L, right? That's the timeless equation for the first step in the journey. Let me call this distance here d. This one, we've got what? We've got vf squared is equal to v1 squared minus 2g times d, right? So here, oh, wait a minute. My bad. You guys tell me what's wrong with this. What's the timeless equation? Yeah. No, go for it.
I was just going to say that v naught is here.
Oh, very true. That's true. This is 0. This is also 0, right? Those corrections are both. I was getting there. Good. There's something wrong with the equation I just wrote, though. What does the timeless equation say? Remember, it says vf squared equals v naught squared plus 2, like the x acceleration times the change in x. But what did we say about the first part of the journey here? The acceleration was what? 2g, right? So I shouldn't have 2g there. I should have what? 4gl. All right, so great. This first equation then gives me v1 squared is 4gl. And then I can take that, plug it over in there, and that gives me 0 is equal to 4gl minus 2gd, which gives me d is equal to what? I'll do an algebra step here. 2gd is equal to 4gl. The g's, they be canceling. And I believe we get 4L over 2, also known as L over 2. That feels wrong. That's got to be wrong. I must have made an algebra mistake here. Yeah, what's 4 divided by 2? Yeah, 2 maybe. Idiot. Me, not you. Let's see here, 2L. I was like, that's weird. Why did it take a longer distance to decelerate? Excuse me, a smaller distance to decelerate than it did to accelerate, but the acceleration was a higher rate. You know, that'd be weird. This should certainly be shorter than d, right? Because the acceleration is not equal there. So it should take a longer distance for it to decelerate, since it's decelerating at a slower rate. All right, so what's the total distance then? Distance total is what? We've got L plus D, which is equal to 2L plus 3L. I mean 2L plus L, right? Which is 3L. So the answer here is 3L. Uh-oh, come back to me. Which? Whew, phew, that's a relief. That's what I got in the notes, 3L. So that's a good sign. All right. So I wanted to spend a little more class time just talking about kinematics. There are more examples in the notes past this, obviously, but it does kind of make me sad. Fine. I'll do one more example just for the sake of sharing with you my art. So I'm proud of these.
You didn't draw that?
I drew that. Of course I drew that. That's my art. No. That is mine. I am the one who invented the prompt to make that appear. It's my art. Right? It wasn't easy. Bing works very hard not to let you throw cats. It's not an easy thing to get it to throw an animal. Like it does take a fair amount of work. I'm too cheap to buy a uncensored one that I could just make, whatever I want happen to a cat happen to it. So here's one. So one final kinematic example, then we're going to turn to Newton's laws, okay? Suppose a cat is thrown by Batman over a river with an initial velocity of 20 meters per second at an angle of 30 degrees, as pictured. The opposite bank of the river happens to rise vertically 5 meters above where Batman's standing, and Batman releases the cat at a height of 1 meter above the ground. If the river is 30 meters wide, will the cat fall into the river full of alligators? So that's the question. Here's the math. So what do we do? Let me find my less bright laser pointer here. So I have I'm told that he throws it at 20 meters per second and he throws it at 30 degrees, right? So I'm basically given the x velocity and the y velocity initially are 17.32 and 10 meters per second respectively after I multiply by cosine and sine of 30 degrees. So there's my initial x and y velocities. I also know my acceleration is 0 minus g because we're assuming this is on Earth and gravity acts downward, right? So that gives me the x velocity is constant, 7.32. The y velocity is 10 meters per second minus 9.8 meters per second squared times time. We put the origin at Batman's feet. So my formula is x is equal to 17.32 seconds times time for the x. And y, on the other hand, is 1 so this is the position of the cat, right? The cat's thrown from 1 meter above Batman's feet. And so it starts out with 1 meter. It's got the initial y velocity is 10 meters per second, see that? And then minus 1/2 gt squared, which is 4.9 meters per second squared times t squared. And then since the river is 30 meters wide, we can find the time it would take the cat to reach the other side by simply looking at the x equation, putting this equal to 30, right? I put 30 is equal to 17.32 times t, and I solve for t, I get 1.732 seconds. Then the question is, what's the vertical height of the cat after that time, right? Given the problem statement, the bank of the other river is 5 meters above where Batman's standing, right? So that would mean that the y for the cat would have to be more than 5 if it's going to land above the vertical face of the river opposite Batman, right? If the y is less than 5, the cat falls to the alligators, as it ought. It's an evil cat. You don't know what it's done, but it's evil. Oh, phew, that's a relief. So what do you know? When you plug in the time, it works out to 3.62 meters, which means that the cat did not make it since it's not above the 5 meter mark. Sorry. If you want less violence done to cats, you should take a different section of physics. I guess I should have warned you that in the first week. I'm sorry I didn't. But it is what it is. Ooh, here's one with Batman on a helicopter. This one, I actually kind of like this one because I like it when my art it does sometimes disproportionately size the cats and morph them with hot air balloons, which is somewhat unsettling.
What am I looking at?
Like,
It's abstract art.
yeah, yeah. All right. Could I like turn that into turn that into some sort of meme coin and like make bank? Would that work? I don't quite understand these things, but all right. This is I did want to talk about this briefly. Here's like a picture of the motion we're studying, right? So like what happens is the velocity is always got the same horizontal component over, right? Whatever x velocity have you at the start, you keep in projectile motion, but the acceleration is the blue vector, which is very boring. It's just minus g everywhere. And it has the effect of what? Turning the velocity going upward to downward velocity as you go on. And that's what happens. I also have a calculation in these notes, which is kind of horrible. I actually calculate the distance traveled for one of these things, and I'm still surprised that this calculation worked out. Like I thought this was going to be. I was originally intending this as a numerical methods example, and the calculus just kept working. So there you go. That's the formula for the arc length of a parabola, given by like projectile motion. This is not on the test, but it's good if you work through it. If it was on the test, that would definitely be bonus. All right. So let me move on here. We talked about this already. So I wanted to, come on. I think if I hit the hamburger, it works better. That's what I was told. Is it this thing? This thing. You guys gave me advice last semester on how to do this. No, that's not what I want.
Now we're down.
Let's see here. Uh-oh. We better get out of there. That's not good. We want to stay out of the memes folder. No good can come of that. What did you tell me? Yeah. We can't have too much flourishing in this class. Let's see here. What did you tell me? How can I get this to go away? This one? The hamburger. Oh, so there's no way to get rid of the rest of the top stuff. It's fine. F11? Well, that says sleep on mine. That feels like a bad idea.
Well, you'd have to FN first.
Yeah.
FN.
The FN F11.
I'm going to be content with this. I think this is fine. So let's talk about history a bit. So I hope I have given you a decent introduction to kinematics. Kinematics is the study of motion in some sense without regard to cause. So I've neglected the question for the most part, why is the acceleration minus beta v cubed? Or, why is the acceleration minus g? Well, I told you it's gravity, but, the reason that we've had the acceleration as it is or the position as it is, that we haven't really focused on, right? So now we're turning the page and starting to look at what's called dynamics. So dynamics is the study of why the cause for motion, right? In particular, it's the study of force. Like that's the answer we give in here, at least for now, is that the reason that there's motion is because there's forces, and forces give rise to motion, all right? That's essentially the Newtonian model. But this is an older story than that, right? The term physics is attributed to Aristotle, who's a Greek philosopher who lived a long time ago, like about 400 years before Christ, right? Something like that. And so Aristotle saw all of matter and its motion in terms of ether and the four elements. You've seen this in various cartoons, right? Fire, water. What's the earth? Was it? What you guys said. So, there it is. Fire, air, water, and earth. I forget. So these elements could be transformed into another, and each had a natural tendency. Rocks fall because they belong on the ground, right? And planets move along their orbits because that's where they belong. Stuff like that. So basically everything's where it is because it's where it's happy. Sounds a lot like chemistry. But anyway, heavier things fall faster, right? Lighter things fall slower. This is still very much the dominant view in like advertising, right? You know full well that if there's a big fat guy getting on, like a water slide, he's going to book it down that slide, right? If he was next to a skinnier person, that skinny person would not go in such a comic speed. So we still very much believe in Aristotle's ideas for for motion as it regards to advertising. So it's not dead by any means. But that was the dominant view of physics through much of the known world from about the time of Aristotle to about 1600 AD. What changed at that point was people started doing experiments, and also we started using math to try to judge the validity or lack thereof of our ideas. One important aspect of that was Copernicus, who he lived 1473 to 1543. He put forth a heliocentric, which that mean? That means helio is what? Sun. So sun-centered model of the solar system. That was at odds with the popular and generally accepted Earth-centered model, which was accepted by Aristotle. And Ptolemy, 100 to 170 AD, he took Aristotle's, like the basic idea that it was Earth-centered, and he gave some further details to that. He made charts and predictions, which actually explained quite a few things. Like people didn't believe in Earth-centered astronomy just because they thought the Earth should be center. It's because this guy named Ptolemy made up charts and predictions that actually seemed to, for the most part, work with observation. So it wasn't just a philosophical thing. It was a matter of pragmatism. It worked, right? Well, it worked up to a point, and it worked up to this point. See, because Copernicus started to realize that no, it makes more sense if you pay more attention to the planets and so forth. You have to take a heliocentric viewpoint. But Copernicus was actually somewhat reluctant to publish his idea. It really only became popular after his death, when it was finally authorized. So it's kind of a complicated business. Now Galileo Galilei was an interesting fellow. He believed also was very conservative in the starting point of his views. He wanted to prove that Aristotle was right, basically, right? And so he set about doing experiments and things to try to show that, yeah, heavy things do fall faster, but much to his chagrin, when he actually tested, do heavier things fall faster, he found no. Actually, whether a thing is heavy or light, it falls in the same way. It falls at this constant acceleration due to gravity. And so Galileo was an important figure. He started to get towards the ground level of Newton's laws. And he's famous for this quote, basically, among other things. The laws of nature are written by the hand of God in the language of mathematics. Galileo is very much responsible for the marriage of math and natural science, which we now know as physics. Physics is a mathematical science at its core. Another important episode in this was Kepler. Kepler took the hard work of an astronomer named Tycho Brahe. Over a period of a decade, he got all this astronomical data, and Kepler wanted to fit that data to circles, but after he looked at it, he found out that actually, if you want to fit the motion of planets, you actually need to use ellipses. All right, and so that gave rise to what we know as Kepler's laws. But this was what we would call a phenomenological model. He just said, well, if you take the data, you can fit it to this formula, right? He didn't give an explanation for why the planet should follow ellipses. In fact, he didn't want them to, because Kepler would much rather have found them to fit into perfect circles, which was more like a philosophical, preference. He also had a deep desire to fit into these Platonic solids. There's like 5 of them. I forget their names, but Kepler's an interesting fellow. So all of this laid the groundwork for Newton. But before we get to that, there's other two. In addition, so physics is one of the things that led to Newton's being able to do what he did. But the other thing that led Newton to be able to do what he did was mathematics and our notation. We take this for granted, but we use numbers, real numbers, right? The invention of real numbers and the notation that we use, more or less, is only about predates Newton by about 50 years. Before then, if you wanted to do calculations with arbitrary precision, you would have had to do something like fractions or prose or something. This unending decimal representation for very small numbers is a relatively modern invention, only predating Newton by a few decades. So if you look at the work of Stephen, and I'm probably saying that wrong, Stephen maybe. So here's some ancient numerals: Shang Dynasty, Brahmi, Indian. So these are like ancient civilizations' versions of numbers. And, here's 16th century, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is relatively recent, this notation, and what predated it was much more clumsy if you were trying to do approximate calculations, which is really the foundation of calculus. Is, in a nutshell, calculus says that the best linear approximation to the graph of a function is its tangent line, right? So the approximation is baked into the cake of calculus, and Newton would not have had nearly as much success if he had to work with different number systems. Ancient mathematicians and physicists, they had to create their own number systems to do very interesting calculations. Like, for example, I don't know if we still have a copy of it or not, but Archimedes is famous for writing this book or article called The Sand Reckoner, where he makes an argument that you could actually count the number of sands on the seashore, because, of course, like philosophers forever since time immemorial said, you can't count the number of sands on the seashore, and Archimedes is like, yes, I can. Here's how. But Archimedes is actually a very interesting character. He did other things like invent war machines that would throw school bus sides things like 2 miles into the sea to defend Syracuse. Why we haven't had a big budget motion picture made about Archimedes yet, I don't understand. It needs to be done. But anyway, and then of course Descartes, or Descartes as most people say. I was in a Rise of Modern Science class, and there was an engineer who called him Descartes, and ever since then I can't help myself. But Descartes, he also was very influential in introducing the Cartesian plane and the Cartesian coordinates, which we have taken advantage of in here up to this point, right? X, Y, Z. The idea that you can make a correspondence between a pair of real numbers and a point. This is Descartes. Without that, we don't know where to start, right? All of these things come together to give Newton the framework to write his laws of motion, right? And so in that sense, Newton would say that he stood on the shoulders of giants, and he wasn't kidding. I mean, it took a long time for Western civilization to get to this point. Now, it is true that aspects of calculus and physics were discovered by other ancient cultures, but it really was Newton and Leibniz who first put forth calculus as we understand it today and made it understandable for common folks like you and me, right? You don't have to be Archimedes to do calculus. We can all do calculus. That's the difference between before Newton and after Newton. But in his masterwork, Philosophia Naturalis Principia Mathematica, which means mathematical principles of natural philosophy, it was written in Latin. He gave these 3 laws. First law, every body continues in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. All right. Second law, the change of motion of an object is proportional to the force impressed and is made in the direction of the straight line in which the force is impressed. Words. And the third law, to every action there is an opposed and equal reaction, or the mutual actions of 2 bodies upon each other are always equal and directed to contrary parts. This is something like a direct translation of Newton's original 3 laws of motion. So Newton was able to use these, plus his universal law of gravitation, to derive Kepler's laws from these basic principles and his calculus. So that's where we are, and most of what we do in this course rests on Newton's work. So we should probably get into it. But these are not the way. We don't want to look at Newton's laws these ways. We have a better way. So here's how we are going to. Our Newton's laws are these. These are the ones you want to know. This is Newton's laws for us, because we don't like translations of ancient Latin work, right? We'd like as close to the mathematics and physics we do in here. These are them. First law, a body remains at rest or in motion at a constant speed in a straight line unless acted upon by a force. That's Newton's first law. See, now we're using words that we've defined in here. Speed, straight line, I don't know if we've defined that in here, but I can define straight line for you if you like. All right, great. Second law, if F is the net force which acts on a body with mass m, then F equals to ma, where a is the acceleration of the body, and that's it. This is Newton's second law is really the main event here, all right? So we're going to base most of what we do on the second law. The third law, I'm not really testing the third law on the first test. We'll get back to testing third law on second test, all right? So my first test this semester, I don't really have free body diagrams so much. At most, we're doing like an equilibrium problem, but we'll get into it here in a second. The third law, if two bodies exert forces on each other, these forces have the same magnitude but opposite directions. So let me put this away, and I'll derive something for you here. If I can get my act together. Oh, no. That was the wrong direction. So like, I guess I should erase this stuff. So one of the things that's weird about Newton's laws is it seems like the second law, implies the first, right? So example 3, assume mass m has net force equals to 0, all right? Let's find the motion. So what are we up against here? We have mass times acceleration is equal to 0. Can we solve this? We can. This is what? This is m dv dt equals to 0. Now, if m is non-zero, what's this tell us? dvd must be 0, right? And we can integrate that. What does it say? The velocity at time t is equal to the initial velocity, right? To say that the time rate of change of the velocity is 0 is to say that the velocity is constant, right? So then what? V is what? The r dt. So if I integrate this, what do I get? I get r of t is what? Time times v naught, right? Plus the initial position r naught. You can check it, right? R of 0 is equal to r naught, right? So now it's just a matter of understanding, what does that mean? If I draw a graph, right? If this is x, this is y, this is z, you know? And this is, say, r naught, that point right here, right? And suppose my v naught goes another way, like this. So this point right here would be something like r naught plus t times v naught, right? What is this blue thing I'm drawing? What happens if you take a point and then you add multiples of one given vector? What do you get? This is a line. So it seems like if the net force is 0, the motion is along a line. But that's what the first law said, right? Unless acted upon by an outside force, right? The motion, it remains at rest or in rectilinear motion, something like that was the so this is in some sense what the first law says. So the second law, in this sense, implies the first. So anyway, We will do more next time. Thanks, guys.